Welcome to a particularly exciting launch with the CAPSTONE vehicle, which is going to be launching aboard an Electron rocket today. And we're going to get the chance to watch along and see how this goes. Yeah, what is going on right now? Basically, there's a little satellite called CAPSTONE, which is going to be going to the moon. And it's a satellite that's been built by, or at least it's been commissioned by NASA. There's another company that actually built the satellite itself. And the goal of the satellite is to essentially go into a lunar orbit and test out some of the things to do with that orbit in preparation for the Lunar Gateway. And the Lunar Gateway is, of course, the big project that NASA is working on right now to help humans get back to the moon. So this is kind of like one of those first steps in that mission. And that first step starts aboard an Electron rocket, which is going to take that payload all the way to the moon. And this also marks the first time that Electron and Rocket Lab will be taking a payload to the moon. So this is going to be interesting for them as well. There are some interesting things about their spacecraft, which is actually uniquely able to do this. And so we will talk a little bit about that as well. And yeah, hopefully we learn a little bit along the way and we get to know about this vehicle and also learn about what NASA's plans are on their way to the moon. So we'll of course have the streams open. Right now we have basically...
Thanks, Daryl. That's right. Welcome to quite literally the future of space exploration. It is just at T minus 51 minutes to the countdown, and here in New Zealand...
So we're just 51 minutes away here, so keep your eyes on the clock there. We're going to be, of course, dependent on things like weather and other things that might come up in the launch. So we want to make sure we keep checking back to make sure that the countdown is still rolling. It's going to be a night launch, so that might be a little bit interesting too to see from the New Zealand peninsula there at the launch complex. But before we get into all that, I think we should probably go over a little bit about the mission and what's going on with the payload itself. So I just wanted to kind of share a little bit about what's happening with the CAPSTONE vehicle. So here we see basically an animation of the CAPSTONE launcher, which is going to go to the moon. It's going into a special type of orbit called a near rectilinear halo orbit. And that's basically the orbit that NASA wants to put the CAPSTONE satellite into in order to simulate what the gateway will be going through. And this little satellite is quite small. Here we have some stats on it. It's just 25 kilograms, and it has a volume of 80 by 40 by 40 centimeters. So you could definitely like pick this up. It would fit inside of like a moving box, basically. The mission duration is going to be about 6 months, so not a super long mission, but that should be enough time for them to do all the science they want to do and check to make sure that this orbit works the way that they expect it to, and that all the communications and other related activities that they can do in that orbit are possible. Yeah, so what is this near rectilinear halo orbit? That's probably a really good question because, coming into this, I had no idea what this was, to be completely honest. I feel like it's just a lot of confusing NASA terms that they use to describe what's going on. So let's go over a little bit about what this orbit actually is and why it's special and, of course, why CAPSTONE is going to it. So here's like kind of a short animation of kind of like what it looks like in terms of the Earth-Moon system. So if you look at it in like from the Earth system, you see basically the satellite is going, through that elliptical orbit up and down, and it creates what kind of looks like a halo, which is why it's called a near rectilinear halo orbit. But essentially what's happening here is the satellite is just in an elliptical orbit, which is what you saw just previously there, where it's basically in a north to south orbit around the moon, where it's coming with its periapsis at the over the northern pole of the moon, and then its apoapsis way down at the southern pole. And what makes this orbit special is that it's kind of using the three body properties of the Earth-Moon system in order to maintain the balance of this orbit. There are Lagrange points that exist around the Earth-Moon system, and these are basically just points in which the gravity between the Earth and the Moon are pulling at the same strength. And so theoretically, if you were exactly in the right spot, you could kind of just hover in that one spot between the two bodies, and they're perfectly stable. The near rectilinear halo orbit is kind of utilizing the Lagrange properties, but instead of holding itself in that one spot, it kind of orbits around that spot. So in a lot of the duration of the near rectilinear halo orbit, the Earth's gravity is actually pulling on the satellite and is causing it to augment its argument of periapsis, which is kind of like the degree to which the orbit is bending. So if you kind of imagine, like, okay, so the near rectilinear halo orbit is kind of like at an angle like this. What will end up happening is that as the satellite orbits around and gets pulled around by the Earth, the orientation of that plane gets changed at the same rate the Moon is actually orbiting around the Earth. So essentially, you can kind of stay with the same face facing the Earth at all times, which makes it really good for communication. And this is one of the reasons why they've picked this orbit. Yeah, it's kind of like a bunch of complicated math and Newtonian physics and stuff to really understand what's going on in this orbit. But basically, it's just really good for making sure that you have, number one, your communication systems pointing towards Earth. But it also gives you, it basically maintains that 100% you can always communicate with Earth. You never go into the shadow of the Moon. And that's kind of the whole idea, right? Because if you want to have people that are, working in lunar space, having communication with Earth is kind of really important. And even if you're just going into the dark of the Moon for 30 minutes or an hour, like something could happen in that time, and then we have complete blackout communication. So this is why it's been kind of selected this way. NASA also claims that this orbit is kind of like special and gives you optimum ability to be able to land on the Moon. I don't know if this is really true, because ultimately it's just an elliptical orbit. So you actually need more energy to get down to the surface than if you were just in like a circular orbit. So I'm a little bit skeptical about that claim. Some of the science that the CAPSTONE is going to be doing is here. You can basically, the main mission, of course, is to verify the characteristics of the cislunar near rectilinear halo orbit. So basically, they want to know how much fuel do they need to maintain the position in this orbit, because it's unstable. Whenever you're in a Lagrange point between the Earth and the Moon, the first three Lagrange points are all unstable, and this is what this one is kind of hovering around. So you need fuel to maintain it. And basically, this satellite is going to kind of verify how much fuel. And that's going to feed into the requirements that are going to be needed for the gateway. They also want to demonstrate basically the communications that they're going to be using on this near rectilinear halo orbit. So they want to be able to communicate between spacecraft, so they have like a spacecraft that goes down to the Moon or does something else. They want to be able to communicate from the base station in the near rectilinear halo orbit to that other spacecraft. So this is important kind of to demonstrate, to see how that works. They also want to kind of also test with their deep space network and how that would work, because once you go beyond basically Earth's communication satellites, you're now using what's called the deep space network. And this is a network set up for all spacecraft that go beyond that point, and they basically communicate through this network of dishes and stuff that are on Earth to look and listen for spacecraft that are really far away. So they'll also be testing that. So yeah, that's kind of an overview of the science goals of CAPSTONE and why CAPSTONE needs to exist. And hopefully NASA will have positive results out of this whole campaign and be able to really come up with a good strategy for how they're going to build the gateway. Let's go back to the stream here.
days to prepare between launch and the time that our team picks up the satellite on the way to the moon.
So tell me, what other lunar orbits were considered when you were first developing this? Because, NASA gave
So here's some
you
more information
the
about the
funding for this
orbits.
mission and
So we
then
should
said,
probably
"Hey,
listen up.
check it out for us."
Oh, sure. Yeah, we looked at a lot of different orbits like this, and they all had to have the same kind of requirements. So they all had to have a low fuel requirement to get this satellite, which only has so much fuel, into that orbit. Has to be a gateway, just like NASA's doing. And then NASA in general has tested out a lot of different orbits. We've landed on this NRHO because of its terrific viability.
And with this spacecraft here, when it maneuvers, it's these small little jets here at the bottom. Is that right?
Yep, that's right. Yeah, it has enough fuel to do everything we need. We have enough fuel for an extended mission as well. It's a monopropellant hydrazine system. Yeah, full spacecraft.
And so in order for it to know where it is, are you telling me this antenna up here is what communicates with the LRO?
Yeah,
Another spacecraft.
That's right. Our spacecraft has two radios, one to talk to the Earth, which is a conventional approach, and one to talk to another spacecraft, the LRO. And this is a reverse radio for LRO, so it's perfect to talk to LRO. We're going to demonstrate navigation in a couple of ways.
LRO is the Lunar
One
Reconnaissance
with,
Orbiter.
Communications with LRO, which should be enough to navigate the spacecraft. Another one to do one-way communications with the DSN, which is a future advanced navigation technology. Everything we can do to try to help enable future lunar exploration.
The DSN
We
is the
envision
Deep
a
Space
future that
Network.
has a lot of missions in orbit about the moon. We're trying to help that out.
They always have so
Absolutely.
many
Thank you for bringing
acronyms
this.
at
This is great,
NASA.
and for describing it, Jeff. But now we're going to go to the real capstone. You see on your screen there, and check back in with the launch team and our
So you can see
commentator,
how small
Muriel
that
Baker. How are we
satellite
doing
is.
so
Like they
far?
can literally lift that up and carry it. It's a really tiny one.
Thanks, Jared. On your screen right now is the Range Control Center, located just a couple of kilometers back from the launch pad itself on the Mahia Peninsula. This peninsula is culturally significant to local Māori people with ancestral ties to the land, so I want to acknowledge first the mana whenua, or the local people, for today's historical.
This is the mission control.
Now, within range control, along the back row of the control center, starting from the
So we're just about 40 minutes away from launch now, and we got a good overview of basically the CAPSTONE satellite, both from NASA and just walking through the orbit that it's going through and some of the details of the probe. So maybe we should talk a little bit now about the Electron vehicle itself. So of course this is a Rocket Lab vehicle, and it's capable of sending about 150 to 300 kilograms of payload into low Earth orbit, but we're actually going into a orbit that's going to take us to the moon. So it's a little bit of a different configuration that they're flying today, but the basic configuration is the one you see here, where they basically have a first stage, which is composing most of the vehicle, all the way up to the very top, which is where you see the second stage, and finally the payload is going to sit right inside of the nose cone at the very top there. Of course, the Electron vehicle is run by the Rutherford engines, which are a very unique type of engine. They're using an electric feed cycle, which basically means that they are using an electric pump to push the fluid into the combustion chamber. And this is a bit unique because it's actually one of the only engines which does this, and it was the first one to do it. There is now a couple other engines that are also using this cycle, but they basically pioneered the whole vision behind this. So here you can see like a typical engine setup on the left, which uses a gas generator engine cycle. Here you're basically using some of the fuel and oxidizer that you push into a pre-burner, and then that energy that you get from burning the fuel in the pre-burner is what drives the turbine that spins the pumps. So you're using some of your fuel in order to run your pump. With the electric cycle, it's a little bit simpler because instead of having all that piping and extra pre-combustion chamber and like exhaust valves and stuff, they just have an electric motor that spins those pumps. So it's actually infinitely simpler. The only issue being that then you need to have batteries that are supplying power for the motor. And battery technology is getting better every day. So Rocket Lab decided that, this is maybe a better way for us. And so, they just bring a bunch of batteries with them. in order to power the motors. So the resulting profile that the mission will have kind of goes like this. So first the Electron rocket will launch, and they'll have 9 engines on the first stage which ignite and start it going on the way to space. Then we're going to have a separation. So the first stage of the vehicle is going to run out of fuel and the engines will turn off. And the second stage will be separated and pushed away from the vehicle. It should be noted that the first stage is not going to be recovered today. We know that the last mission that Rocket Lab did feature a recovery with the helicopter that they were using to catch the first stage. However, today I don't believe they'll be catching that first stage. So that one's just going to fly back into the ocean. They still are working on the whole recovery regime, so they're not recovering every single mission at this point yet. Then we're going to have an ignition of that second stage, and that second stage will take the payload all the way into an orbit around the Earth. But just before that happens, we're going to have a payload fairing separation, and that's basically the protective covering that's over top of the CAPSTONE vehicle to protect it from the aerodynamic forces going through the atmosphere. But once the second stage ignites, we are already out of the atmosphere, so they can get rid of that extra mass of those payload fairings, so they'll be separated. There's also going to be what's called a battery hot swap, which basically is because the engine is running on these batteries with that electric motor, they don't want to take all the batteries into orbit with them because, again, that's extra mass. So what they do about 2/3 of the way into that second stage burn is they're actually going to release that battery, and it's going to basically fly away, and then they don't have to take all that mass with, dead batteries to orbit. So just another thing they do to make it a little bit more efficient. Then once we arrive in orbit, the photon upper stage is going to separate, and that photon is basically the little yellow golden piece of the rocket that you see there. The photon upper stage is going to be the vehicle that's going to power the CAPSTONE satellite into the lunar orbit. So the second stage just gets us into an orbit around the Earth that's in a low Earth orbit. And then basically the photon upper stage is going to take over, and it has rockets on it and solar panels and all kinds of systems and stuff, which it will use in order to send that CAPSTONE satellite all the way to the moon. And the way it's going to do that is kind of looking like this. So it doesn't really have a lot of power, that photon upper stage, so it kind of has to do multiple firings of its motor in order to modify the orbits that it's going into. And finally, at the end, it'll have an orbit that's big enough to get all the way to the moon. So it's going to kind of do it in multiple passes. Yeah, that's going to take a little while. It's not going to happen all at once. So this will probably be a process that takes a couple of days in order to get all the way out to the moon. So we're not going to be able to witness all of this today, of course. But we will see all the way up to the release of the photon upper stage, and we may get to see the first ignition that it does in order to raise its altitude a bit. So that's kind of the profile of the vehicle that we're going to see. So definitely look out for these things that are happening during the stream, and hopefully you can recognize what's happening relatively well. So yeah, that's just a bit about the profile that the mission is going to be going on. We are just over T-minus 30 minutes to launch, so we should be getting into some of the interesting fueling and other types of things. If we just switch back to the stream here.
Thank you again for being here. Well, we've showed you how CAPSTONE is a Pathfinder mission for NASA's Lunar Gateway. As NASA astronaut Randy Bresnik will show you, the planned orbiting lunar outpost is the first step to fulfilling plans for a more permanent presence on the moon.
Home. For me, home is where my family is. But there have been times in my life where I was called away from my family for extended periods of time. While I was serving in the Marine Corps, it was hard to be away from my loved ones. But thankfully, I had my squadron family but other places where we were stationed around the globe became a temporary home. Then, in 2009, I launched the International Space Station, traveling even farther away from my family, conducting science 250 miles above the Earth. The space station was an orbiting home for my crewmates and myself. Talk about a room with a breathtaking view. With Artemis, NASA will send the first woman and the first person of color to the moon. We are going there for the benefit of
Artemis is basically the end goal here, right?
We'll need a place
And
to orbit
the
around
lunar gateway.
where we
So
can live and work, a place to get ready for our lunar surface expeditions, and a place to return to when our work on the lunar surface is complete. We need a lunar home away from home. This will be the gateway. Starting with the power and habitation modules, the gateway will be the first long-term outpost in lunar orbit humans have ever had. Primed for new discoveries, this orbiting laboratory will provide us with a unique view of our solar system. And it's already becoming a beacon for the future of international and commercial cooperation in space. With increasing capability and longer missions over time, the gateway will be a powerhouse of technology and science, paving the way for future human missions to Mars. Design and fabrication of gateway elements by NASA and our international partners is well underway around the world right now. Wherever you are on planet Earth, today you are part of the Artemis generation. I'm NASA astronaut Randy Bresnik. I invite you to join us by following NASA Gateway on social media and telling us where you call home.
it'll definitely be exciting to see.
T-minus 31 minutes and counting until launch in New Zealand with our NASA Mega Moon rocket here on the ground as a backdrop. It's time now to dive into the details of CAPSTONE's orbit, the near rectilinear halo orbit. I spoke to Jude Moranci, chief of the NASA Exploration Mission Planning Office, about it.
So we should get an overview of
Jude
the
Moranci, thank
halo
you for
orbit
being
now.
here. We're launching, of course, CAPSTONE today, a microwave-sized CubeSat that's going into this near rectilinear halo orbit. Eventually, it will lead the way for Gateway, a much larger lunar outpost where astronauts will go. What's the difference between getting CAPSTONE into that orbit versus the lunar gateway?
One of the really interesting things with the orbit mechanics is we can sort of play with, how much propellant it takes to get somewhere and the time it takes. So CAPSTONE is using a ballistic lunar transfer. So it'll take 3 months to get to NRHO, but it'll use a quarter of the delta velocity that we'll need when we fly this with Artemis and the crew. So the crew will only spend, 5 to 10 days in transit. We'll fly very close to the moon and use the moon to slingshot us out there, but it takes more delta velocity or, relative propellant amount. So, we can play with both the time and the duration to get into NRHO based on whether we're flying crew or you're doing something so uncrewed like the CAPSTONE mission.
And looking at this near rectilinear halo orbit, you can see it really goes quickly around the moon, but spends more time away from it. Why is that, and are there advantages or disadvantages to that?
Yeah, so the NRHO, or near rectilinear halo orbit, it's an elliptical orbit. So when you're close to the moon, the spacecraft, any spacecraft will fly very fast. You'll go over the north pole of the moon in about a day, but then we spend about 6 days over the big part below the south pole of the orbit. So you go very fast close to the moon, slow when you're away from the moon. But the reason we're in this orbit is it's incredibly stable, but also relatively close to the moon. So with that stability, we only need the equivalent of 10 meters per second of delta velocity for a whole year to maintain the orbit, which is very small in spacecraft terms. So that means we can put the Gateway there for 10, 15 years and not need a lot of propellant to keep it there. But it's also close enough to the moon that the human landing system can access the South Pole. We can do the human exploration in the future, as well as have that stability for a good outpost capability. So really it was that balanced orbit for the long-term planning of Artemis and the objectives we need for human exploration.
Oh, that's very interesting. And so what is required in order to maintain that very unique orbit? Is it difficult?
So the orbit should be relatively easy to maintain, but that's why we want CAPSTONE to go first so we can collect all the data and validate the models. So it doesn't really matter what size the vehicles are, the orbit mechanics will work the same. So with CAPSTONE as the sort of pathfinder, it can demonstrate the navigation, the guidance, the propulsive capability to maintain the orbit, and we can really just extract from that the math to validate the orbits for Gateway, Orion, and Artemis missions. So the maintenance of the orbit is really fascinating, easy thing to do, so we can use these two missions to compare how they work. But the other advantages of this orbit is it's very stable for power and thermal and has continuous communication with Earth. So, you know, the operations in this orbit are really good for that long-term deep space exploration capabilities that we want to demonstrate.
Najib Moranci, thank you so much for your time today.
Thank you for having me.
So there you go. You have a nice explanation for what makes the near rectilinear halo orbit special. Basically, there are a couple of things. The first of all is that you have an orbit that actually brings you close to the moon so that you can perform deorbit burns relatively easily. But also, as she said, you have less delta V that you need in order to maintain that orbit. As I said before, the near rectilinear halo orbit is unstable because it's going through basically around, it's working around the three body properties of the Earth-Moon system. So those things tend to be obviously not fully stable. However, you don't need a whole bunch of fuel in order to maintain it, only 10 meters a second. Maybe you might consider, well, why wouldn't we just go into a low lunar orbit? Like that should be stable as well, right? But the problem with that is that it's actually less stable than it seems. If the moon was a perfect body and a perfect sphere with perfect density, then that would be obviously the best move to go because you would be infinitely stable. Kind of like if you're playing like Kerbal Space Program or something and you're going around the moon. If you pick an orbit that's in low moon orbit, it'll just stay there forever, right? Unfortunately, the real moon is not exactly as perfect as that, so it's lumpy. And what this essentially causes is that if you're in a low lunar orbit, the lumpiness of the moon is actually causing your altitude to decay over time, and you'll crash into the moon after, sometimes it can happen as quickly as just a couple of months. So, yeah, they figured this out when they were in the Apollo era, when they were trying to do orbiting around the moon. But of course, they didn't really care so much then because during the Apollo era, you just do your little, you do the mission in a couple of days and come back. So it didn't really matter so much that the orbit wasn't fully stable. But of course, if we're going to have a station there, it's a little more important that we have a presence there that is easy to maintain. So the Gateway's planned to be there for 10 plus years. We don't want to have to keep bringing a bunch of fuel in order to maintain a relatively unstable orbit like the low lunar orbit. So that's why they come up with this near rectilinear halo orbit, because it balances out basically the energy it takes to maintain that orbit and the proximity that it still maintains with the moon so that they can perform a deorbit burn. They do need a little more energy to come out of that than you would for a low lunar orbit, but I guess that they balance that against the energy they need to maintain an orbit like this, and they said, it's better this way. Although I would like to see that math. It would be interesting to analyze. So that's kind of the summary of what it's all about, and basically CAPSTONE is going to be going and trying to verify that specific orbit. And verify that they only need the 10 meters a second per year in order to maintain it, because of course if they find out that it's more, then they may have to revise their plans a little bit. All of this, of course, is all done in supercomputers, and there are still things about the moon's gravity that are not fully understood because they don't have a bunch of missions that are running around the moon calculating the exact potato-ness of the moon's density. So there are still things they need to figure out, basically. So we're getting a bit closer now to the launch. We'll keep checking in with the live stream as we go here, but it looks like they're still doing Rocket Lab promotional stuff. Of course, Rocket Lab is the vehicle that's Rocket Lab is the company that's going to be launching the CAPSTONE satellite into this orbit. It's going to be using its Electron rocket to do this, along with its Photon upper stage. So the Photon upper stage is a bit special because it's the only small sat launcher which has this type of capability on it. It's basically just a satellite bus plus some propulsion systems that can take your satellite from anywhere in space to somewhere else. So the Electron vehicle will get the CAPSTONE satellite all the way into orbit, but then the Photon upper stage will take over, and it will then power the CAPSTONE satellite into the lunar orbit that we're trying to go to. That'll take a couple months. And just to reiterate, the way that it does this is by basically boosting the altitude of that orbit slowly over time. And as was just mentioned, that's going to take a process that's going to take about 3 months. So they're kind of taking their time with it, and as they were saying, this means that they can save a little bit on the fuel because they don't need to make that burn all at once, and they can kind of use the gravity between Earth and the moon to kind of help pull them towards the moon, essentially. And then they save on fuel, but it takes a bit longer. But it's fine if there's no people on board because you don't have to like feed them or anything. So yeah, that's kind of the way that they've planned this out. When humans go there, it probably won't look like this. They're probably just going to go with a much bigger rocket, and that rocket will fire once and get them all the way to the moon relatively quickly. So it'll be like maybe just a 4 or a 5 day trip, kind of like how it was in the Apollo era. Yeah, really looking forward to that happening. When they're streaming this at NASA from the basically with the backdrop of the rocket. You can see it right there. It's in the backdrop. That's the Artemis rocket that's just sitting there on the launch pad, and that one's going to be going pretty soon. So hopefully this is a quick precursor to what NASA should be doing quickly in the future.
Thank you, Daryl. So to get the spacecraft out of low Earth orbit and on a ballistic lunar transfer to the moon, for the first time Rocket Lab is using its lunar configuration of our Photon spacecraft bus. Now, unlike the Apollo lunar missions of the 1960s and 70s, which took a free return trajectory to the moon, a fuel-efficient ballistic lunar transfer makes it possible to deploy CAPSTONE on a distant orbit using a small launch vehicle. The first 9 minutes or so of the mission will follow the typical mission profile of an Electron launch. The rocket will complete liftoff, first and second stage separation, and finally end with Photon separating from Electron's second stage in an elliptical orbit. Now that is where things start to get interesting, because once separated from Electron, Photon will carry out a series of orbit-raising maneuvers using its hypercurie engine, stretching its orbit into a prominent ellipse around Earth. About 6 days after launch, a final burn from the hypercurie engine will accelerate Photon to 24,500 miles per hour, enabling it to escape low Earth orbit and set CAPSTONE on a course for the moon. Within 20 minutes of the final burn, Photon will release CAPSTONE into space for the first leg of the CubeSat solo flight, and then CAPSTONE's journey to NRHO is expected to take around 4 months from that point. Now,
4 months, even more than 3 months.
Inserted into the orbit, CAPSTONE is expected to remain there for at least 6 months, allowing NASA to study the orbit's dynamics. Now, here are 2 pivotal members of our Photon team to explain more about our Photon lunar upper stage.
My name is Ehsan Mosley. I'm the Chief Engineer for Space Systems at Rocket Lab.
I'm Rich Hunter, and I'm a Mission Design Engineer on the GNC team.
My job is to oversee the entire technical progress of the mission between conception to delivery of the 12U CubeSat to its end destination.
I do mission design and flight dynamics for CAPSTONE, and I combine all that into a picture of what Photon and Electron are, and use that to design and optimize trajectories to get us from LC.
Okay, so yeah, that was a quick overview of what the Photon upper stage is basically doing. Basically, it's a method that Electron uses in order to allow them to go further. One of the limitations of an orbital launcher is that basically it's difficult to move. They kind of optimize the vehicle in order to get as much payload as they can into low Earth orbit. So if you want to go much beyond that, you have to kind of reduce the mass. You can reduce the mass of your payload, but you run into a limitation because, well, the second stage of the rocket itself has a bunch of mass. So if you compare the mass differences, like for the CAPSTONE, we saw here that the CAPSTONE only weighs about 25 kilograms. So basically, Rocket Lab is capable of delivering 300 kilograms into low Earth orbit. So the difference between 300 kilograms and 25 kilograms is, only 275 kilograms. Whereas the mass of the entire second stage of the rocket is, when it's dry, is, definitely hundreds of kilograms. So that the difference there is not significant enough that you get really that much more delta V out of the rocket equation. So in order to compensate for this, you can kind of add a third stage, which is basically what this photon is. It's a kick stage for that CAPSTONE satellite. And basically that's adding a bunch of fuel onto that third stage that will then go into the rocket equation and allow it to go a lot further than if you didn't have it and you just use the second stage itself. So you'll often see payloads that are going beyond like geostationary orbit. They usually need some sort of kick stage. I think almost every rocket uses it, unless you're launching on like an Ariane 5 or something. Ariane is kind of a special vehicle which is able to get really, really big delta Vs just because it's using hydrogen and oxygen as a fuel source. That one and also Atlas V, it also has some good characteristics. Although for the satellites that go really far, like for instance the satellite that went to Pluto, it also needed the kick stage to get out that far. So kick stages are common when we're sending payloads out beyond the orbit of Earth. And here we can finally see the Electron on the pad.
Today's mission to the moon. Our talented and dedicated team have been making their way methodically through.
And you can see here that you see those like white bands on the rocket. So the rocket's actually entirely black. And the reason why we have these white surfaces on the rocket is simply because the water in the air, like the humidity in the air, is actually condensing on the rocket and freezing. The reason why that's happening is because the rocket's being filled with liquid oxygen and also RP1. But the liquid oxygen is stored at minus 180 degrees Celsius. So it's really cold. And basically when the air, comes near the tank at such a low temperature, that's what's causing the water basically to freeze out of the air and be deposited on the rocket. And that's how you know that they're basically fueling the rocket. You'll see these vapor clouds that are coming off, and you'll see basically the ice that's on the booster. The vapor clouds aren't bad. That is also a result of the liquid oxygen that's being filled into the vehicle. Basically, liquid oxygen needs to stay at minus 180 degrees Celsius inside of the tank, but of course it's not minus 180 degrees Celsius outside. So the liquid oxygen is always evaporating a little bit. And if you didn't let that liquid oxygen out, the pressure would build up and build up and build up inside of the tanks and potentially blow up the tanks. And you definitely don't want that. So they always vent the liquid oxygen into the air, and that again, the humidity will condense out of the air, and you'll get water droplets, and that's what's making the clouds.
GC.
GC is go.
PLS.
PLS is go.
So we have our no-go poll now.
RSO is go. MET.
MET is go.
MM.
MM is go.
Tank.
Tank is go.
Prop Charlie.
Prop Charlie is go.
AV Charlie.
AV Charlie is go.
Ecom.
Ecom is go.
C2.
C2 is go.
Fighter.
Fighter is go.
LD Sub.
LD sub is go.
On all stations, that is the go-no-go sequence complete. We're currently T-minus 14 minutes, 8 seconds and counting. We'll go for terminal count start at T-minus 10 minutes. Be advised from this time the 3-word procedure is in effect.
Looks like we are fully go. And the
there
three-way
we
procedure
go. That
is
a clear run through.
the three-way procedure just means that you have to call hold, hold, hold 3 times, and then that means you have to stop the count. So just to clarify. So we've passed the no-go poll. Everything looks like it's go, and we're probably looking like we're probably going to see this one launch today.
So let's go back to the Kennedy Space Center in Florida, where Daryl is with another special guest.
Thank you, Muriel. Got all the times covered. Appreciate that. Joining us now is Justin Treptow, Deputy of the Flight Opportunities and Small Spacecraft Technology Programs, to talk about how small businesses played a large role in this mission. Justin, great to have you back. You used to work here.
So he's going to be talking about the company that
Now
actually
up at
built the
headquarters,
CAPSTONE
but
vehicle.
Back in Florida for this launch.
Absolutely. I'm extraordinarily excited to be here for our lunar mission.
First question, why does NASA partner with small businesses like the ones that were involved in the CAPSTONE mission?
Well, it's an interesting interplay between government and commercial companies. With spacecraft getting smaller and more capable, we're seeing more entrants getting into the space industry. And as they get more and more experience on orbit, they're demonstrating real capabilities that NASA can partner with to lead missions like CAPSTONE and really take a leading role in gathering data that we can use for other projects. This spools into the ability to have those companies turn those capabilities into services that you can buy as another government organization or other parts of NASA. We heard an interview with Rocket Lab earlier talking about their Escapade mission. Mm-hmm. They developed the lunar photon, which is being used for another NASA mission, which would not have come to pass if it wasn't for the CAPSTONE mission. We wouldn't have the data for Gateway to take advantage of if Advanced Space wasn't here as a commercial partner on this project to bring the data from one project to another project.
That's fascinating. So you mentioned some of the benefits already that have been gained. And we've seen that through the development of CAPSTONE, right? Because NASA says, hey, go develop this. And then if there's spin-offs that are beneficial in other areas, you're starting to already see that with CAPSTONE?
Yeah, absolutely. Some of the examples, like one of the most obvious ones, is with the CAPSTONE propulsion system itself. Having a high delta V propulsion system on a CubeSat form factor is something that is, in the small sat world, kind of the holy grail. Being able to go somewhere and actually do something of value is really useful. And having Stellar Exploration develop a propulsion system that CAPSTONE's using to get into orbit around the moon in the NRHO and to stay there for an extended period of time is a propulsion system that's showing up in other commercial products that's infusing within the industry. So we're seeing the technology that NASA's funding for our missions go into other places within the space industry.
Already, so quickly, early on in this. That's impressive. We're now T-minus 10 minutes and counting until the liftoff.
So you can see how NASA is continuing to try and develop the space industry, even through this type of a mission, by supporting Stellar Industries, I think is the company that is making the CAPSTONE satellite. So you'll see the system that they use for propulsion probably in the future on other missions, just because it's somewhat innovative to have such a relatively higher delta V system on a small CubeSat. So, and getting a CubeSat that can go that far is also quite unique. I don't think we've actually ever sent a CubeSat to the moon, so this could be a first as well. But just to go over, I just want to quickly go over the launch sequence again for those who may have joined a little bit later. So of course we're launching aboard the Electron vehicle, and it's going to go through a couple of key moments. So first we're going to have the launch, which is happening in about T-minus 10 minutes. And that's when all 9 of the Rutherford engines will light and begin the ascension into orbit. Then there's going to be a separation of the first stage from the vehicle after the first stage has run out of fuel. And this will happen about 3 or 4 minutes into the flight. The first stage will basically just come back to the ocean and crash into the ocean. There's not going to be a recovery attempt today. I know that the Rocket Lab did do a recovery mission the last time they flew with there and back again. That was mostly successful. They just dropped the stage back into the ocean once they had already caught the booster. But today they're not focusing on the reuse aspect of the rocket because I think they're still going through data and trying to set up a mission which will have a fully successful recovery. Think about it like the old days with SpaceX. They didn't recover every single stage they did after the first test. So unfortunately, this one won't get recovered. But the second stage will continue onto orbit. It will basically ignite a couple seconds after it separates from that first stage. And then right after the ignition, after some seconds, the payload fairing will separate. And the reason for that is basically the payload fairing is protecting the CAPSTONE rocket and the Photon upper stage from the aerodynamic forces of the atmosphere. But once you're up high enough, which the second stage will be at this point, you can basically get rid of those payload fairings because they're not really useful anymore. And they're just weighing you down. The second thing that's going to happen at this point, a little bit later in the burn, is there's going to be what's called a battery hot swap. So, of course, those Rutherford engines are being powered by electric motors. So they need electricity, but batteries are super heavy. So the second stage is really kind of trying to stay mass efficient. So about 2/3 into the burn, it actually just jettisons 2/3 of its batteries in order to save on mass, because those batteries are dead anyway, so you don't need them anymore. So you'll hear them talking about battery hot swap, and you'll see, maybe if you look carefully, the batteries flying off the vehicle. Then you're going to have the separation of the Photon upper stage from the second stage of the vehicle. That's going to happen about T-minus 9 minutes. And then finally, over the course of the next couple of days, you're going to see the increasing of the orbit with that Photon upper stage. We may see the ignition of the one ignition of the Photon in the stream, but I'm not sure if it'll be held for that long. And yeah, the Photon will basically increase its orbit a little bit at a time, and this is going to take a process of many weeks, and it won't arrive at the moon in the orbit that they want to be in for about 4 months. So really a long time. You wouldn't want to take humans on this type of a trajectory because, yeah, you probably wouldn't be able to feed them for all that length of time in the capsule. So that's not the part that the CAPSTONE is trying to demonstrate. They're basically just going to verify the orbit that's actually going to be around the moon. And just to reiterate what that orbit is, it is a near rectilinear halo orbit, and basically it's this elliptical orbit around the moon. And if you look at it from the Earth frame, it kind of looks like this, where it's, you know, going up close to the moon and then coming down to the lower part of the elliptical orbit. And basically, if you draw out the path that it takes around Earth, it looks like a halo, which is why it's called this. And this is basically a special position where they will always have communication with the Earth, because the plane of the orbit never allows it to go behind the moon. So you can always communicate with the Earth, and that's kind of one of the main reasons why they're on it. And also it's relatively stable. They don't need that much fuel to maintain this orbit, and they're relatively close to the moon for at least part of the orbit, and they can perform deorbit maneuvers and land on the moon. So it kind of is the best of all three worlds, so to say. All right, we are just T-minus 5 minutes. Really coming up to the last bits here.
Launch Complex 1, where we have 2 orbital launch pads within our private spaceport dedicated for Electron launches. Now, Rocket Lab launches typically deploy spacecrafts to orbits between 500 and 1,200 kilometers altitude above Earth's surface. But this time, as you'll know, Electron and our upper stage Photon will send the CAPSTONE spacecraft a little bit further than usual, some 1.3 million kilometers further. Around 9 minutes after liftoff, Electron's second stage will separate from Photon, placing the spacecraft bus and its CAPSTONE payload into an initial low Earth orbit of just 165 kilometers. Now, from this initial parking orbit, Photon's Hypercurie engine will perform a series of orbit raising maneuvers over 5 days to stretch its orbit into a prominent ellipse around Earth. Now, 6 days after launch, Hypercurie will ignite one final time, accelerating Photon to allow it to escape low Earth orbit and set CAPSTONE on a course for the moon. From there, Capstone's journey to NRHO is expected to take around 4 months, with the CubeSats team at Advanced Space's Mission Operations Center commanding the spacecraft to fire its thrusters to adjust its course accordingly. Now, if we are looking back at the pad camera now, we can see that the rocket's strong back has retracted and has moved into the launch position. This launch platform structure is what holds the umbilical lines, providing power to the rocket, which will fall away as Electron lifts off the pad. You can see Electron's icy white stripes on the outside of the rocket there too. Those are because of the super cold liquid oxygen propellant on the inside of the rocket, which freezes water on the outside, causing it to form those distinctive icy areas along the rocket's black carbon composite body. Now, our last weather update also confirmed that the wind speed at T0 is expected to be good for launch, further minimizing the weather risk to today's mission. Now, as we get closer to the countdown, it is worth pointing out what kind of views to expect from launch today. As always, we'll be bringing you the live views you see on your screen from various cameras at the pad and at range control. However, for this mission, we won't have the typical onboard vehicle cameras you might be familiar with for Electron launches.
Oh no.
And that is because this mission has extensive telemetry requirements. So to reduce the load on systems and operators, we've streamlined the mission down to essential systems only. Now, while
No
we won't
live
have those
streaming
live
from the
vehicle
rockets.
feeds to show you, we will be broadcasting mission data and animations, so you can keep up with the launch progress throughout the ascent.
This is one thing I like about Rocket Lab is they put a camera on their second stage as they go up, but I guess we're not going to get to see the live view today. Understandable though, because they do have lots of telemetry requirements that Capstone is having on it. Plus, they're operating that the Photon upper stage. So yeah, better that they get it right than give us a nice view. But hopefully, the tracking cameras are able to see lots with this being a night launch. So at least you should be able to see the flame of the rocket. So we can at least cover that.
10 seconds and engine ignition at T-minus 3 seconds. We'll hand over now to mission control and listen into those calls to launch.
Launch vehicle is fully on internal power. Lunar Photon is on internal power.
So they've just retracted the umbilical that gives power to the vehicle, and now it's powering itself.
Recirculation.
So
anti-gathering disabled.
In the final minute, the rocket is now in its, basically it has control over the systems. So if it sees anything that it doesn't want to see, it will also be able to call a hold.
Stage 1 and Stage 2 at rest.
High flow engine purge enabled. What a deluge activated.
T-minus 20 seconds.
All right, here we go. Looks like it's a go.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
And she's away. All right. First mission to the moon for the Electron rockets. And first, I think, also CubeSat to the moon. Everything's looking pretty good so far.
Stage 1 propulsion is nominal.
So the rocket's going to go through maximum dynamic pressure pretty soon.
Entering burnout detect mode.
where it's going to be just passing the speed of sound, and that's where the most drag on the vehicle will occur. This is usually a pretty significant event, just for structural reasons.
Crank shipper on one.
But it looks like they're not putting the speed and altitude data on the screen. Oh, here it comes.
1 minute and Electron is in the air and onward
So
to the moon.
they just passed max Q.
That rocket is soaring through this nighttime sky, now past 14 kilometers in altitude in these past few moments. Now things look to be continuing nominally, which means that shortly Electron will come up against max Q, or maximum dynamic pressure. Now this is the moment when Electron will experience its most amount
This
of
already happened,
stress
so
as it travels through the
they're a little bit
atmosphere.
behind.
And I can confirm from mission control that we have had max Q confirmed, so that was a successful pass through that milestone, and Electron is onward to low Earth orbit. So propulsion appears nominal on that first stage, and the Photon lunar upper stage and CAPSTONE spacecraft remain healthy inside the rocket's fairing. We are coming up soon on 3 events in the launch timeline that will occur in very short succession. So soon, the 9 Rutherford engines powering Electron right now will diminish their power and then shut off completely. That command is signaled by the rocket's flight computer and then called across mission control comms as MECO, or main engine cutoff. Now once that action is complete, Electron will separate its first and second stages. The main booster will continue to slow and remain behind while the second stage carries on with the mission with the ignition of its single Rutherford engine. And we have had MECO
we have MECO.
confirmed, and will be coming up soon.
And again,
on
we-
the fairing separation
we don't
for
have
the
that
mission. So just
second
to
stage
confirm for
camera.
mission control comms, we have had MECO.
We don't have that second stage camera this time because of the telemetry requirements for the rocket, so we just get this animation instead. And we're going to get...
Preparation of this mission, that is the jettison of the fairing halves or the rocket's nose cone that sits on top of the second stage. So now that Electron is well past the Kármán line, we don't need that fairing. It served its purpose to protect the payload and the Photon upper stage during the launch through Earth's atmosphere. So again, that fairing will separate shortly in preparation for the final stage separation between the second stage and Photon. So there we go, we heard it on comms. We have had fairing separation on that second stage, and so there's confirmation that mission is continuing as it should, with CAPSTONE and the Photon lunar upper stage now exposed to space and no longer needing that protection through Earth's atmosphere.
we got a nice
It's very
view
exciting to
of
see
the
this mission
CAPSTONE
up
satellite
and
at
in the
least.
air. And if you have just joined us, we have had a great start to today's journey to the moon. We have successfully cleared the pad at Launch Complex 1 just a few moments ago, and we are now well on our way to space, having completed that first successful pass through max Q, main engine cut.
So the main thing to look out for now is on the altitude and the speed indicators. So the speed we need to get to is about 27,000 kilometers per hour. So that'll be signifying that we are in an orbit. We also probably going to be targeting an altitude of somewhere in the range of probably somewhere in the range of 180 kilometers or so to 200 kilometers. So they're going to be moving basically into a nice low Earth orbit. So yeah, that'll take a little while, but yeah, the animation is not really meaning anything at this point. But the altitude and velocity indicators are coming straight off the spacecraft, so that's at least communicating to us real information. Unfortunately, as we said before, they weren't able to put a camera on the upper stage, or at least I'm sure they still have the camera, but they're not streaming the camera because of the high telemetry requirements that they have for the rest of the vehicle. So because they have the Photon upper stage and they have the CAPSTONE vehicle, there's kind of lots of things that need to be streamed back to the Earth on the telemetry system. So unfortunately, the camera showing the vehicle is not a priority. But yeah, it's going to take us about 3 or 4 minutes to finish this burn. And then we're going to see the separation of the Photon vehicle from the upper stage of the spacecraft. We'll just see it in the animation, but we will have confirmation via the altitude and velocity sensors.
Stage 2 guidance remains nominal, 200 seconds remaining.
So just over 3 minutes left in the burn.
If we take a look at the graphics on the right-hand side of our screen, we can see the measurements for the propellant on Electron. So on your left, you have the kerosene propellant and the level of the tanks that it is now at. So we're at 45% and counting, sitting at a nice and warm 8 degrees in temperature. And that is very warm compared to the liquid oxygen temperature, our other propellant. So that is sitting at a nice and chilly minus 178 degrees with 40% or so propellant left.
It's pretty nice that they show that animation of the propellants. I think that's kind of cool.
Hot swap.
It's making it look very SpaceX-y.
And there we have the call
Stage
that
two,
battery
Russian
hot swap
is
on the
nominal.
second stage was successful. Now, next we should expect to hear one of our operators in mission control call out that Electron is orbital, indicating that the rocket is in the right place ahead of stage separation. So SECO, the acronym for second engine cutoff, and the subsequent stage separation follow relatively the same procedure as main engine cutoff, where the Rutherford engine on the second stage will shut off ahead of the final separation of the vehicle between the second stage and the Photon lunar upper stage. There will be a bit of a gap between that final separation and the first hypercurie burn, as this stage separation places the Photon lunar upper stage in an elliptical orbit of Earth first. Now, a reminder that 165 low Earth orbit is just the first orbital phase for this CAPSTONE mission, with Photon and CAPSTONE's orbit continuously raised higher and higher over the next few days with a series of engine burns on the upper stage. I'll go into more detail about Photon's phasing orbits and CAPSTONE's path to the moon shortly, once Electron has completed SECO and stage separation. Let's listen into mission control comms.
We're getting close to the end of the burn here. You can see there the fuel and the oxidizer are just about out, and we're nearing the target final height of the orbit. Again, the target speed they're getting to is 27,000 kilometers per hour. So you really can see the velocity equation in effect here, because just that little bit of fuel at the end really gets you a lot of delta V. And I also like this readout because it kind of feels a bit like Kerbal Space Program when you see the how much fuel you have left. They should do that with the actual camera on the upper stage as well.
Altitude of this mission, we are traveling at more than 23,000 kilometers an hour. And while on the right you can see the altitude is at 175 kilometers, what goes up must come down, and we will lower ourselves into that 165 kilometer parking orbit very soon.
So they're a little bit high. So just a couple seconds here, we're going to see that second. There we go. It's shut off.
SECO confirmed.
And Photon is deployed.
So with the Rutherford engine cooling down, that tells us that second engine cutoff was successful on Electron's second stage. And the Photon lunar upper stage has now departed into its low Earth orbit with the moon-bound CAPSTONE spacecraft on board. Now, as a reminder from here, Photon is in charge of the mission. With its relightable hypercurie engine, Photon will begin maneuvering into a parking orbit just above substantial atmospheric drag, but below the Van Allen radiation belts. It is the perfect, stable platform from which to prepare for lunar departure. Now, once Photon is in the correct orbital alignment, the hypercurie engine will ignite again, performing a burn to lift the highest point of Photon's orbit, the apogee. Now, as it gains altitude and also loses velocity, and so what goes up comes back down as Earth's gravity pulls it back towards the planet. When it reaches the lowest point, or perigee, once again Photon's hypercurie engine ignites to increase velocity and raise its apogee higher. So if you've ever been on a swing set, swung to the top, came back down.
This is looking a lot like the diagram that I made here. So basically every time the satellite's going to get to the periapsis of the orbit, it's going to perform another burn. It's going to push a little bit higher, and then a little bit higher, and then a little bit higher. And basically this is kind of the orbital paths that it's going to make as it's boosting itself on the way to the moon.
Precision translunar injection burn, accelerating the upper stage and capstone to a top speed of nearly 11 kilometers per second, fast enough to break free of low Earth orbit on its way to the moon. The speed Photon is traveling at this point will shoot it well past the moon's orbit and to the edge of the Earth-Moon system on a transfer orbit. Lined up with the sun and using its gravitational pull to shape Photon's orbit to match speed with the moon, CAPSTONE will then be deployed and carry on the mission solo. And so with those first few hypercurie burns scheduled in the coming hours, I'm going to send it back to Daryl and the team at the Kennedy Space Center. Daryl, I know you weren't here in person, but how was that for you guys over at KSC? My heart is still...
All right, so it looks like we have a successful launch. We basically have got the Photon upper stage into orbit, so that's good to see. We've also been able to have a successful launch of the Electron rocket. There were no issues on the launch. They went into the orbit that they wanted to get into. The Photon upper stage will carry on its way into the moon over the next couple of days. So definitely stay posted on Twitter or social media, however you want to follow the mission. Both NASA and Rocket Lab will be posting updates on this. The Photon upper stage is still the part of the Electron vehicle, so that's still, Rocket Lab is still touching it at this point until they deploy it into the orbit around the moon. So that they'll be basically there for the next couple of months. And the beauty about the Photon upper stage is that it's actually able to perform these types of operations. It's essentially a satellite in and of itself, and it really allows it to be able to take things, CubeSats and stuff like this, into very different places, even beyond the orbit of Earth. So I would be curious if they could also use this to like get to Mars or something. It could be quite useful. So it's a good demonstration of this technology that Rocket Lab is using here. So you can see that Rocket Lab does more than just make launch vehicles. They also make satellites and upper stage, kick stage type vehicles that can basically take you from Earth to anywhere. So a really cool part of Rocket Lab's development process. And it's great to see that unfold on the screen today and watch as they successfully develop this type of technology. So really happy for Rocket Lab. I'd like to thank you for joining us with this live stream. And of course, I hope that you continue to expand your horizons.